Hi, this is Sachin Patil. I'm going to present in detail the embedded firmware and other system components section of Chapter 2 of Introduction to Embedded System by Shibu KV. So today in this session, uh, we are going to cover the embedded firmware and other system components. We learn about the embedded firmware and its role in embedded system. And in other system components, we try to understand the different components like reset circuits, brownout protection circuits, the other units, oscillator units, real-time clock, watchdog timers, and even PCB, role of PCB in embedded. So as you all know, you're all surrounded by a number of embedded systems, even in home or in when go outside the in market or in traffic control system in hospital or in a bank. In any of the supermarket, if you go, there's a point of sale systems. In all these are we are surrounded by embedded system. All of you know the embedded systems are built around a system core and 6 different components connected to make the embedded system. So among them, the other system components and this embedded firmware, and to mount all these components, the PCB are very important for us in the design and building of embedded systems. So today we'll see the other system components and embedded firmware. So embedded firmware is a software program what we write to make the component, peripheral component like sensor, actuators, and other interfacing components to make work according to the requirement or a function of an embedded system. It's a control algorithm what we write in the form of program instructions, and we configure the settings required for embedded system developer, and to avoid the part of an embedded system. This is a there are various methods available for development of embedded firmware. There we can write a program in a high-level language just like C, C++, using embedded integrated development environment. For example, for 8051, we used and for ARM microcontroller for Cortex M3. We use Kyle company's Microvision soft ID, and write either one more choice is we can write in assembly language program using the instructions supported by the target processor. We have to understand the machine code before loading it into the program memory, and the process of converting the high-level language, the program what is written into machine understandable code is called as an hex file creation. If the program is written in embedded C or C++ using the IDE, the cross compilers are used to convert the code into the high level code into a hex file which the machine can understand. So with this slide it will all the whatever I explained about the embedded firmware will get clear. So either the program is written in C or C++ or a language, the first it can be converted, should be converted into using the cross compilers to assembly language, the target board specific code, and then into machine understandable uh, machine language code in the form of binary. So you can see that the three different files. There's a program written in C, program written in assembly language, converted to assembly language, or written in assembly language. First, at the end, it is converted into machine language in the form of binary zeros and one, so that the embedded system will work according to the instruction written in the form of program. So other system components, we're studying reset circuit, brownout circuits, oscillators, and which are essential for functioning of the processor or a controller, which is used in embedded system along with the around the processor and the controller. The embedded systems are developed. First, we'll see the reset circuit. A reset circuit, the an integrated internal registry and the different hardware systems of the processor to the known state and starts the firmware execution from the reset vector. So these are the circuits which either it may be active high or active low. The device will set to its default values internals, so the program execution starts from the beginning. So this reset pulse should be wide enough to give time for the clock oscillator to stabilize before the internal reset state starts. So these are the few reset circuits. Some circuits are built internally, do not require any external reset circuit, and some are required. Yes, some are connected externally. And this R and C in all these reset circuits will set the pulse width of the reset circuit. So how much width that time is given to reset all its internal registers of the processors. That depends on this R and C in this circuit. Next one is a brownout circuit. So the brownout circuit is nothing but a protection circuit for embedded system. So if any variations in the supply voltage or it might either fall below the specified voltage, then the embedded system sometimes behaves abnormally or unexpected program execution behavior it shows. So this brownout circuit holds the processor circuit reset state in the reset state, and if when the voltage falls below the threshold. Certain processors supports a built-in brownout circuits, and some need to be connected externally. Nowadays, most of the embedded systems, the brownout circuits are inbuilt. Next one component it is must or essential for the synchronizing the operations of the processor internal blocks is oscillators. So even the oscillator circuits are in some embedded systems are built in. So we need, for example, here where I'm showing the moving the cursor, that you can see this block diagram. So where the oscillator circuit is inbuilt, the only thing we need to connect externally the crystal torch for supplying this clock signals. And then another block diagram you can see the externally we have to connect the oscillator circuit. So the everything is clock signals are supplied from the outside. So real-time clock. So real-time clock is a circuit. It's with connected with the backup of a battery cell. So that circuit will keep a track of a day, time, a month, year, a day of a week, etc. and supplies the timing reference to the embedded systems. Some embedded systems need the day accurate time, date or month to be maintained. So that's why even in the absence of the power supply also, that we have to keep a track of or update these all parameters. So in such cases, this RTC will help us the synchronizing the operation of the kernel. This RTC is used. It is a single IC package. Watchdog timer. Watchdog timer is a monitor the firmware execution and it will reset the system. This will be better understood with example. So for example, if anything happens in the laptop, for example, if the laptop hangs up, then we have a reset button. Then we can press the reset button, that the system will again reboot and start functioning properly. And even we have the option Alt Control Delete. So we'll go to text that it will take it to task manager, where you can kill some of the tasks, and then again the system will resume. This kind of option is not there in the embedded system. For example, MP3 player, for example, mouse, remote. If you press the in a short time more buttons on the remote, sometime this may hangs up. So we don't have a provision in the remote for to reset and all, just like a laptop. So in an embedded system, there is a circuit for a firmware is executing, that there is a clock is set. Then if any malfunction happens, and then the hangs up the even some program that is executing, firmware executing in the embedded system, for example mouse and all, if then the counter which is set inside in the program itself, it will go on updating even if it hang up. And when the count exceeds the maximum count, then the processor will be reset, so that the embedded system will again start reboot from the reboot or function properly. So here they have shown this is the slide will give clear idea, but how the watchdog timer is a free running counter which will reset the controller, and the embedded system will resume its work from where the point where it hung up blocked. Next is and this the PCB. So printed circuit, what we call it is a printed circuit board, is a backbone of every embedded system. So because this PCB act like a platform for mounting all the necessary components as per the design. First we draw the schematic on the PCB board, and then we do the etching, and then the components are mounted. The components, just like the co-workers of various chips, like register, relays, and etc. With this, this finishes the part 5 of embedded Introduction to Embedded Systems, Shibu KV, Chapter 2.